14th International Physics Olympiad 1982 year IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. Email fred1996@hotmail.com. Skype name Edward F. 1996. Problem 1. Jumping particle. 8 points. Jumping particle A moves along the positive axis OX, one-dimensional situation, under a force that's projection on OX is Fx equals F0 as represented in the figure below, as function of x. At the origin of OX axis is placed a perfectly reflecting wall. A friction force of constant modulus Ff equals 1.00 newtons acts anywhere the particle is situated. The particle starts from the point x equals x0 is equal to 1.00 meter having the kinetic energy EC equals 10.0 joule. Question A. Find the length of the path of the particle before it comes to a final stop. Question B. Sketch the potential energy Ux of the particle in the force field Fx. Question C. Draw qualitatively the dependence of the particle speed as function of his coordinate x. Solution for problem 1. Question A. Find the length of the path of the particle before it comes to a final stop. It is possible to make a model of the situation in the problem, considering the OX axis vertically oriented having the wall in its lower part. The conservative force Fx could be the weight of the particle. One may present the motion of the particle as the vertical motion of a small elastic ball elastically colliding with the ground and moving with constant friction through the medium. The friction force is smaller than the weight. The potential energy of the particle can be represented in analogy to the gravitational potential energy of the ball, mgh. As is very well known, in the field of a conservative force, the variation of the potential energy depends only on the initial and final positions of the particle, being independent of the path between those positions. Since the ball is constantly subject to a force directed toward the wall and there is a friction force, the final location of the ball will be point x equal to 0, thus, all the kinetic energy of the particle plus potential will eventually go into the work of the friction force. That is, the relationship is true, Jf0x0 equals Ffd, where d equals Jf0x0 equals 20 meters. So, we have calculated the total distance based on the simple principle of energy conversion. Now let's calculate it based on ordinary kinematics. Apparently, we will have to calculate the sum of the terms of the geometric sequence. Option number 1. The initial velocity of the particle is directed upward. Then the total force acting on the particle will be F plus equals F0 plus Ff, that is, 10 plus 1 is equal to 11 newtons. Since the initial energy of the particle was J equals 10 joules, then the height to which the particle rises above the initial height x0 is equal to J divided by F plus or 10 divided by 11 meters, and the total maximum height h0 will be equal to 1 and 10 divided by 11 meters. Now the particle begins to move downwards. But now the force acting on the particle will be F minus equals F0 minus Ff which is 9 newtons, therefore, the kinetic energy of the particle before colliding with the wall will be E0 equals h0 times F minus equals 9 h0 joules. Now let's calculate the next height h1, to which the particle will rise. This will be E0 divided by F plus equals 9/11 h0, thus, we have calculated the coefficient of the geometric sequence, k equal to 9/11, and thus we can calculate the sum of the series of the geometric sequence starting from the first member. Of course, it must then be multiplied by 2, since the particle passes each height up and down. That is, we get the following sum. 2 multiplied by h1 and multiplied by the bracket 1 plus k to the first power, plus k to the second, and so on ad infinitum, which as a result is equal to 11h1. Now remember that h1 is equal to 9/11 h0. That is, the total result of the sum will be 9h0, but h0 was equal to 21 divided by 11 meters. Therefore, in meters we get 189 divided by 11 meters. It remains to add to this sum the initial h0 equal to 21 divided by 11 meters and the initial segment 10 divided by 11. We get that d is equal to 189 plus 21 plus 10 in the numerator and 11 in the denominator, which is exactly 20 meters. This gives us the result as in the case of a simple application of the energy conversion formula. It remains to consider the case when the initial velocity of the particle is directed downwards. I think now you know how to do it yourself. Question B. Sketch the potential energy U as function of x of the particle in the force field Fx. The relation U from x equals Fx by x gives the linear dependence of the potential energy to the position. If the motion occurs without friction, the particle can reach a point A situated at the distance delta apart from the origin in which the kinetic energy vanishes. In the point A the energy of the particles is entirely potential. The numerical value of the position of point A, furthest away from the origin, is delta equals 2 meters if the motion occurs without friction. The representation of the dependence of the potential energy on the position in the domain 0 to delta is represented in the figure. Figure during the real motion of the particle, with friction, the extreme positions reached by the particle are smaller than delta, because of the leak of energy due to friction. The graph in the figure is the answer to the question B. Question C. Draw qualitatively the dependence of the particle speed as function of his coordinate x. Solution. During the motion of the particle its energy decrease because of the dissipation work of the friction force. The speed of the particle has a local maximum near the wall. Denoting Vk the speed of the particle just before its kth collision with the wall and Vk plus 1 the speed just before its next collision, Vk greater than Vk plus 1. Among two successive collisions, the particle reaches its xk positions in which its speed vanishes and the energy of the particle is purely potential. These positions are closer and closer to the wall because a part of the energy of the particle is dissipated through friction. Xk plus 1 less than xk. Case 1. If the particle starts from the x0 position moving in the positive direction of the coordinate axis OX its speed diminishes and its kinetic energy also diminishes while its potential energy increases to a maximum in the x1 position where the speed vanishes. During this motion the energy is dissipated due to the friction. The total energy Wx, for the positions x between x0 and x1 verify the relation Wx0 minus Wx equal Ff multiplied by x minus x0. The position x lying in the domain between x0 and x1. When the particle moves from x0 in the positive direction of the axis, the relation becomes next expression. So we have. Using provided data we have. The graph in the figure presents the dependence of the square speed on the position for the motion in the domain x between x0 and x1. The particle moves in the positive direction of the coordinate axis OX. This motion occurs until the position x1, when the speed vanishes, is reached. From the previous relation, in which we take the modulus of the speed 0, results x1 equal this expression. The numerical value for x1 is 21 over 11 meters. After furthest away position x1 is reached, the particle moves again towards the origin, without initial speed, in a speeded up motion having an acceleration of magnitude a minus equals fx plus ff over mass. After the collision with the wall, the particle has a velocity v1 equal in magnitude but opposite direction with the one it had before the collision. When the particle is at a point lying in the domain between 0 and x1 running from x0 to the origin, its total energy Wx has next expression. Because of friction, the value of the energy decreases from the one it had at x1 to the corresponding to the x position. We have the square of the speed has the expression. And the speed is. For the given data, in the domain, 0 to x1 speed square equal. Respectively speed is The speed of the particle hitting a second time the wall according to previous is and has the value. Concluding, after the first collision and first recoil, the particle moves away from the wall, reaches again a position where the speed vanishes and then comes back to the wall. The speed of the particle hitting again the wall is smaller than before, as in the figure. Denoting Vk the speed at the beginning of the kth run and xk the coordinate of the furthest away point during the kth run, the energy of the particle leaving the wall is. In the position xk after the k departure from the wall, the energy is. The variation of the total energy has the expression. So that after the particle reaches the position xk the direction of the speed changes and, when the particle hits the wall, the energy conservation law for the xk position and the point in which the particle hits the wall gives. So that considering previous, this relation becomes. Between two successive collisions the speed diminishes in a geometrical progression with the ratio q. Using the data provided we have q equal. From k plus 1th collision the previous relation is written as. Considering these two, the ratio of the extreme positions in two successive runs is. For the kth run towards the origin, one may write the dependence of the square speed as function of the position as. Or, using the data we have. The evolution of the square of the speed as function on position is presented in the figure 1.10. And the evolution of the speed as function of the position is presented in the figure 1.11. The sum of the geometrical progression gives after the doubling and then subtracting of the x0 the total distance covered by the particle is. It results. The total distance covered by the particle is. Which allows us to find again the previous result. This was the solution to question C in the case of the initial direction of the particle's velocity from the wall. Similar reasoning can be applied during the initial movement towards the wall. This concludes our discussion of task number 1.